Hi guys, and welcome to today's lesson on the Truncus. And as you can see there are some fabulous pictures of elephants, slightly multicolored, and if I saw a multicolored elephant, I'd probably be concerned that something I'd eaten wasn't necessarily good for me. But having done a most amazing African safari where I got to ride elephants, it was amazing. All right, so one of the highlights of my life so far, I'm sure. And those of you in internet land can completely ignore this little section here that is effectively for those people cursed by my teaching in the physical form in the classroom, because those are the questions I'm going to want you to do. Everyone else, just sit back, relax, and hopefully by the end of this you will have a fabulous understanding of trunci. We've already dealt in a previous lesson with relation to rectangular hyperbolas. And as I've stated over and over again, once you know what the base graph of a function looks like, you can use transformations to help you move things around. So, rectangular hyperbola, if you didn't watch that lesson, it was a stunner. It was great. Otherwise, come and join me today when we're dealing with the truncus, which will leave two more graphs to deal with. That's the square root graph and circles. Rather differently than the last time I did this, let's go straight in with what a truncus looks like. And as you can see there, it looks like a volcano or some sort of trunk of a tree or something along those lines. The base equation is given by y equals 1 over x squared. Now, automatically, my brain is going x squared. I've got that x on the bottom again. What happens if I put x equals 0 in? Well, again, if I put x equals 0, I'm going to have 1 over 0 squared, and 0 times 0 is 0, and as such, that means I'm going to end up with an undefined value. Likewise, when I put y equals 0 in, because when I rearrange that, I once again end up that x squared is 1 over 0. So, because I can't put 0 on the bottom, it would suggest to me that I have asymptotes. And as we can see, yes, there we go. Ladies and gentlemen, my two asymptotes are x equals 0 and y equals 0. Why are there no negative y values? If you look at this graph here, do you see it doesn't actually go below the x-axis? And again, you can infer this, or you already know this, because when you square a negative value, what actually happens to that negative? Well, a negative times a negative becomes a positive. And so that explains why this graph doesn't, in its untransformed state, go below the x-axis. So that's also really, really important. And it ties into my domain and range. So domain are my possible x values. And if we look at it there, what can we not have? We cannot have 0. We've already decided that. So we would write real and not 0. My range in this situation is really important. It can't go negative, so we can't have minus infinity to anything. It obviously can't have y as a 0 value, because that basically doesn't work either. And so again, in this situation, we put just r plus. R plus means all positive real values, and because 0 is neither positive or negative, or it's both, or it's one of those, we'll narrow it down. Then we just leave it as r plus. So that's my domain and range, and again, that's always really, really important. Helpful points, yes, here we go. Here are my helpful points, 1, 1, and minus 1, 1. Really, really important to remember. Is my graph now awesome, and can I get hundreds of marks in an exam for this? Absolutely not. Why? Because I have not labeled my asymptotes. So I have an asymptote at x equals 0, I have an asymptote at y equals 0, and ideally I should write onto my function 1 over x squared. Are there any axis intercepts? There are not. And so, ladies and gentlemen, there is my base truncus. And as I say, for all of the 4 main graphs you're going to deal with, you really should memorize this. And for a piece of useless information, the plural of truncus is in fact trunci with a single I. And I think of truncuses, and I think of elephants, and I think, oh, bless the little hearts. Okay, so we now know that all of these functions can be transformed. And here we have 1, 2, 3, 4, 5, 6, 7 different functions. Now, my advice to all of you out there in internet land is that for each of these individual functions, you should always try and break down what each of them is asking you to find. This one here is obviously my base, so I know what that looks like because I will have memorized that. This one here, really important. Anytime I multiply my base function, which is 1 over x squared, by a constant, and that's the same as multiplying it by 3, this value here is effectively my dilation away from the x-axis. So that number on the top there, that 3, is my dilation away from the x-axis, because I've taken that whole function and multiplied it by 3. I've changed all my y values to make them 3 times bigger. Here, I have a translation. In this situation, it's going to move 3 units that way. It's inside the function. It's inside that squared. It means it's doing the opposite. It's got something to do with the x. So it's a translation in 3 units. And they get more complex. Number 4 here. Let's see, what do we have here? That 2. I now know that's going to be a vertical dilation factor 2. The 1 is going to move it 1 unit to the left because it's negative. You know, +1 means do the opposite. And this +4 means 4 that way. Now you can see that I'm circling and doing arrows. Why? Because it helps me break this stuff down. That's the whole point of doing it. Planning for when I actually draw these functions. This situation here is a factor of 4 dilation away. Now this here is a bit of a trick, a big fat trick, right? Lots of people think, oh, that's a dilation factor of half and then a translation of -3. Sadly, it is not, and please don't get confused. I'll come back to that a little bit later on. And finally, what's the difference here? Well, a negative there would be a reflection in my x-axis, and this is a massive trick here. That is going to be actually a reflection in my y-axis, but we shall not rush things there. Why? Because we just need to take a tablet and just calm down. So, remember order of transformations? In my previous lesson, we looked at the idea of Dr. T and Mr. T, that very muscly, terrifyingly large guy from the A-Team back in the 1980s. But Dr. T is what we actually need. So Dr. T states we do dilations, reflections, and translations. Now, that is true only if the order is not given to you in the question. If they actually ask you to do reflections, followed by dilations, followed by translations, that's what you have to do. Okay? Otherwise, dilations, reflections, translations. Let's kick straight into reflections of trunci. Wow! When we reflect said trunci, and again, make sure you always remember what your base truncus looks like. All right? This is a very, very brief sketch. I'm going to reflect that in the x-axis. Here is my x-axis, which means that it's actually going to reflect that way. And lo and behold, there we go. Yes, we can see that it just flips. Now, important information, same as with rectangular hyperbolas. When you are reflecting or dilating, the asymptotes do not change. So that's awesome. So I can automatically write down my asymptotes are x equals 0 and y equals 0. So there's y equals 0 and there's x equals 0. And my helpful points now, because we're reflecting the x-axis, my y values will go negative. Okay? Or if they're already negative, they go positive. So just be careful there. There we go. 1, -1. And -1, -1. So there are my helpful points written on there. I need to do that for my examiner. My domain and range in this situation, well, the domain stays the same. If we look at all the possible x values that can go in, all values can go in there except the 0. It doesn't really matter that it's -1 over x squared. If I make that 0, we're going to end up with dividing by 0. It's not possible. But my range, if you remember, for the standard trunci, my range was r+. So if I'm flipping it, and that meant all positive real values, then flipping it, I use /r-. And there's this alternative method here. Now again, it's always a good idea to write the domain as that, and the range as that, and then r, what did I say, /0, and in this situation r-, and don't forget the 2 little lines for your r. Right, that's great notation. And once again, remember that shape. So that's reflection in the x-axis, and I'm pretty sure all of you will be aware that if I want to reflect in the y-axis, well, if my original shape starts like this, and I'm going to reflect it in the y-axis, then, well, actually, it's just going to be the same shape. All right? Not particularly complicated. Don't spend too much time. Asymptotes stay the same. Helpful points stay the same. Range and domain stay the same for my standard. Now, just to prove why, there we go. We have y is equal to 1 over -x squared. You're going to say, well, why is it -x squared? When you reflect in the y-axis, you take your original function, which is y equals 1 over x squared, and you replace x with -x. So y becomes 1 over -x all squared, which when you square out a minus and a minus becomes 1 over x squared. And hence, that explains why it is my original function. As is always normal, I would then label my x and my y and my asymptotes. x equals 0, and I'd put my equation on there, which is actually 1 over x squared, and I would write down any axis crossing points, but again, because this is just a basic reflection, there aren't any. So that's reflections done. Then we go to D for dilations of the trunci, right? Dilations can take a place away from the x and from the y-axis, and this is going to take a little while to explain. Fingers crossed I can do it in less than 5 or 6 minutes, but first things first, let's deal with dilations away from the x-axis. As I said earlier, when you have a function of x, if you have the original function as 1 over x squared, then that would suggest that 3 over x squared is my original function times by 3. Well, that's the situation when I multiply my whole function by a value, then that suggests it is a dilation away from the x-axis. Why? Because all this value here is doing is changing my y values. 1, 1 would become 1, 3 in that situation. And yeah, lo and behold, there we go. There's my helpful point. I've dilated this away, factor 3 from the x-axis. My x values haven't changed. My y values have. My asymptotes won't change either. Remember, dilating away will not change my asymptotes. So if a question asks me, I'd write on my asymptotes, or I'd absolutely write them on my graph. So that's y equals 0 there, and x equals 0 there, and my important points and what have you. Domain and range, do they change when you dilate? No, they stay exactly the same as they would for the base function, unless you're doing a number of transformations. But in this situation, we're not. So that is our beautiful dilation from the x-axis. Now, I would always recommend you trying to get a function so that you have some form of multiplier times function of x. So for example, if I had 9 over x squared, I would know that that was my original function times 9, which is a factor of 9 away. If I could get my function to be 4 on 3 x squared, for example, then I would know that that is the same as 4 on 3 times my original function. That in itself, being fractional doesn't actually matter, is a dilation of factor 4 on 3 away from the x-axis. Yes, the 3's on the bottom, but actually it makes life much easier if I can move that and have that fraction outside. Why? Well, let's have a look at this question here. Dilation of factor A from the y-axis. Now, if I have a factor of 1/3 from the y-axis, if you remember your algebra, you remember that when you are dilating from the y-axis, you replace x with x on A, where A is your scale factor or your dilation. So that means that I have, my original function was 1 over x squared. I'm now going to replace that with 1 over x on 1/3 squared. Now, many of you are already looking at it going, oh, no, that's horrible. Yes, it absolutely is. I'm going to change that to 1 over. Now, when I do x divided by 1/3, and when I've got x over 1/3, I'm going to write that out longhand. It's x divided by 1/3. And keep, change, flip means that x divided by 1/3 is exactly the same as 3x in brackets squared. Whoa! Which, going back to what I said a moment ago, if I was to square this out, I'd actually end up with 1 over 9x squared, which is the same as 1 over 9 times 1 over x squared. And as I've said, if I can have a fraction multiplied by my 1 over x squared, that is a dilation of factor 1/9 from the x-axis. Well, hold on a moment. What do you mean 1/9 factor? We were dealing with factors from the y-axis. Yes, I know. But what I'm trying to tell you is that dilations from the x-axis and dilations from the y-axis can be exactly the same, just depending on how you write the equation. So as I say here, 1 over 3x squared would suggest, by looking at this here, that you have a scale factor of 1/3 away from the 1/3 away from the y-axis, whereas if I write it as 1 over 9x squared, that tells me that it's actually 1/9 away from the x-axis. And if we check, what I've noticed here, that this point here is 1, 1 over 9, and yet this here is 1/3, 1. Same graph, but this now proves that I've actually factorized by, I've dilated by a factor of 1/9 from the x-axis. This one, factor 1/3 from the y-axis. Lots of this comes down to personal preference. I always try and get things to have a fraction here. And again, I'll come back to that in a little bit later on. But having a look at this now, having done the dilation from 1/3 from the y-axis, having done my algebra, either to get it to that stage there or that stage there, I can then go on and sketch this. And I have to say my helpful asymptotes are 0, 0. My helpful points are 1, 1/9 and -1, 1/9. Domain and range, because it's a dilation, doesn't change. Now, again, need to be very careful here. And there is a huge difference between the graph of 1/3x all squared and 1/3x squared. Okay, so be very careful here. In this situation, that would multiply out to give you 1/9x squared. Whereas this would stay as 1/3x squared. So this would have a scale factor or a dilation of factor 1/9, and yet this one would stay as 1/3. They are not the same graph. Translations, easy peasy lemon squeezy. When you translate, the asymptotes change with the translation. So horizontal translations will change your x asymptote, and vertical translations will change your y asymptote. So nice simple example here. We've translated a factor of 3 that way, or 3 units in the positive x direction, or parallel to the positive x direction. And the language is really important here. So translation to the x-axis. And in this situation, you'd put positive or negative. So what's actually happened? Nope, that was not right. +3, doofus, actually goes that way. So it's 3 units that way. And in which case, what were my original points? My original points were 1, 1 and -1, 1. If I'm moving it 3 units that way, it's my x values that are going to change. I can take 3 away from each of those, which gives me -2, 1 and -4, 1. So, and there we go, -2, 1 and -4, 1. Love it when a plan comes together. We would need to make sure in this situation that we label that as x equals -3. We would need to make sure we label that as y equals 0. We'd need to make sure that we put the label by the function. But we now have an x-axis intercept, sorry, a y-axis intercept. So when we have a y-axis intercept, what do we need to do? We put x equals 0. So y is equal to 1/x plus 3 all squared. We have to put our x value as 0. So that would become 1/3 squared, which becomes 1/9. And lo and behold, I would then need to put 0, 1/9. You must label those points. Right? My advice is always to write the coordinate beside them. I wouldn't necessarily just put 1/9 on the x-axis and hope the examiner can do it. So that was translation parallel to the x-axis. And again, no difference to translation parallel to y-axis. In this situation, that -2 means that it actually works in the direction I'm expecting. Going to move the whole thing down. So y is equal to -2. X is equal to 0 in my asymptotes. Thank you very much. My helpful points in this situation have gone from 1, 1 and -1, 1. I'm moving those down 2 units, so it becomes 1, -1 and -1, -1, which is where we are showing my 2 beautiful points. Thank you very much. And in this situation, what do I have? Oh, shucks. I have 2 x-axis crossing points. When that happens, I put y equal to 0. So if I have my equation 1/x minus 2, 0 becomes 1/x minus 2. Add 2 to both sides gives me, sorry, I keep doing that, it's x squared. I don't know why I keep missing those squares. I'm becoming square dyslexic. 2 is equal to 1/x squared. A little bit more manipulation. And that gives me x is equal to plus or minus the square root of 1/2, which can be rewritten as plus or minus the square root of 1 over the square root of 2, or more simply, plus or minus 1/√2. And again, here I would be putting my x value as 1/√2, 0, and here I'd be doing minus 1/√2, 0. Now, don't in an exam, particularly in mathematics in Australia, write these as decimals. They have to be exact form, and so you are looking at having them including pi's, e's, or square root signs if that's the case, okay? So please don't make that mistake. Write those coordinate values on. Lastly, combining transformations of rectangular hyperbolas. Yes, in this situation, I said we would look at it as, you know, something complicated. There are lots of ways of doing this, like lots and lots of ways of doing this. So first things first, if I try and break this down, I've got a 4, so I know that that's going to be parallel, a dilation away from the x-axis. I've got a -3, I know that's going to move it down 3. It's this bit inside the bracket that I think you need to be the most cautious about. That is not, it is a dilation factor a half away from the y-axis, but it is not a translation of factor 3 parallel to the x-axis, right? It is not a translation of power, and that's where people make mistakes. First things first, if you want to do it that way, you always need to have the coefficient of x to be 1. Whenever you can get your coefficient of x equal 1, then you are pretty much on the right line to being able to do this. So if I move over here as an aside, I'm going to write that as 4. I'm going to write this as squared brackets because I want to keep my squared there. But to get 2x to have a coefficient of 1, I've got to factorize out the 2. So that gives me x. But by doing that, I'm then got to half everything. So that becomes 3 on 2, -3. Now that it's written in that form, where this whole section here is inside the squared, so I know I'm dealing with a truncus. Because I've got my x value here now with a coefficient of 1, then I can now confidently say that yes, this is going to be a dilation factor a half, opposite of what you're expecting, from the y-axis, but now it's going to be a translation of actually 3 on 2 that way, -3 units that way, and 4 units dilation. Now, that's a lot of work, like a lot of work. As far as I'm concerned, crazy. Why on earth would you want to do that? But there's actually an easier way of doing it. So how would I do that easier? I'm actually going to go one step further and multiply out that bracket. Right? We have 2x plus 3 on 2 all squared. Now, if you go back to your square rules with a, b squared, when you have two things inside a set of brackets squared, that's exactly the same as a squared, b squared. You can take each thing and square it. So I could rewrite that as 4x plus 3 on 2 squared. I haven't actually changed the base of my graph. It's not making things any different, but look what now happens. I have 4 over 4x plus 3 on 2 squared minus 3. And I happen to know that 4 divided by 4 is 1. So my much simplified function becomes that, which actually means I've turned 1, 2, 3, 4 different transformations into actually 2. This graph here and this graph here are identical, I promise you, and I'll show you in a second. But now, by doing that tiny bit of algebra, all I've got to worry about doing is moving my original function 3 on 2 that way and down 3. OMG, mind blown. So much easier. All right, so there we go. That is my original function. If we look at the crossing points, and all my asymptotes, actually, if you compare it with the simplified, exactly the same. So once again, sorry, scrolling up and down all the time. Here, I've got 4 separate transformations to try and get me to what actually, with a little bit of algebra, would have taken me to just moving the graph to. Now, yes, you would still have to do the algebra to find out the crossing points. You'd still have to put x equals 0 and y equals 0 into this function. But just one more time, if I can, I would always try and turn my function so that it is an a times f of x. Always try and turn it so I can take the whole function and multiply it by one dilation from the x-axis than having to faff around with other things. Anyway, long video, 25 minutes long. I'm getting longer, but this is really important. Thank you so much for taking the time to watch. Hopefully it's made some sense. I look forward to seeing you next time. Joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, Take care. See you again soon.